now, the microphone. Okay, great. So, okay, let's move this. Cool. Okay, hi everyone. This is one of the talks in a series of talks I do called Functional Pearls. If you've seen it before, this isn't actually the same material at all, so I'm doing entirely different stuff. And this time around, I'm going to talk about purely functional data structures. So before, I've done versions of this talk at EPVOL, the London Pearl Workshop, and at YAPSI EU, and also Northwest England Pearlmongers. And I've spoken about things like currying, doing references to operators like plus or minus, using monads in Perl, using a model called Acme monads, which is mostly vaporware, but does actually kind of work, and various crazy crack using Devel Declare that Matt Trout wrote. But this time, we're going to talk about, we're going to learn some Italian. So we're going to learn how to say ciao. But this is, these are two ways of presenting the string of letters, ciao, obviously hello or goodbye in Italian. And we're going to look at, first of all, the version on the top, and then finally we're going to look at this list at the bottom and see how we'd implement them. Now, if you've already done any data structure stuff, a lot of this may seem quite simplistic, but it's a 20-minute talk and we can only cover so much. So hopefully it'll give a taste of things. Now, this is a classic way of representing a string of letters in memory, and it's called an array. So you start off with a contiguous block of data in memory, and at regular offsets you store each character. So very simply, if you want the 0th element, you just start where the block starts, at position 0, and you have the letter C. And if you wanted the second, obviously we can also change and update data in the array by simply writing over the data there. So we can change ciao into meow. Now obviously this is mutating data, and because we're talking about purely functional data structures, we tend to think of actually changing data as being harmful. So I would like to point out that no kittens were harmed during the making of this presentation, just in case anyone was worrying about that. But we will try and see if we can find a better way to update things without actually mutating the data structure. So we can access the second element by simply taking an offset of 2 boxes along in data in memory, and we get the letter A. So it's actually very, very fast to get any element of this array. Now, if we try to get the 4th element, which doesn't exist, what's going to happen? Now, in a very naive way, and I think you can achieve this in assembly language or C or very low-level language, you might get garbage data that just happens to be sitting in memory of the computer somewhere, and it's entirely meaningless. Or, if your programming language is a little bit more sensible, it'll realize that you're trying to read data that doesn't exist, and it'll throw an error. Now, in order to do that, of course, it means that the data structure is a little bit more complicated. It has to store not just this area of data, but also the length that it's currently got. So we already looked at how you would change a value of this string. But what if we wanted to extend the string to the right? Now obviously there isn't any more data there. There might be another data structure in memory right next to it. But if we had an extra space on the end that we didn't use, we still labelled that the string is only 4 elements long, i.e. the max position is 3, but we have a little bit of extra space. So we can now change that into meow with a W on the end. Fantastic. But what if we wanted to write even more data than that? Now obviously one way of doing it would be to have every array can have 100,000 empty bytes of data in order that we can carry on adding to it, ad infinitum. And obviously that's going to be a little bit inefficient at some point. So what a lot of programming languages will tend to do is you'll have some data spare so you can update with a certain character. If you want to update with more information, then the programming language will actually create an entirely new array, which is even bigger and has a few more extra spaces on the end of it, copy the information that you've already got into that structure, and then add something to the end of it. And at that point, you can throw away the old array. So that sounds quite complicated, but it's actually what Perl arrays already do, more or less. I'm eliding over details and waving my hands very fast. But so this is what the arrays that we use every day know and love do. So why would you want to consider any other way of saying ciao? So let's have a look at those. So this is one of the earliest data structures that was ever invented back in the 70s, and it's one of the simplest possible structures, because you basically have a whole load of elements that have a piece of data, like C or I or A or O, and also a pointer to the next element. So for example, C points to, C has a head, which is C, and points to that list there. It doesn't know about all the other characters, it just knows that there is another list somewhere in memory that will also have a head and a tail. So we can go down the list following the tail and get into a new list every time. Now with an array, we could index into it and get the 0th, the second, the whichever element straight away in one opcode. Here, we can get the 0th element very easily, but if we want to go further down the list, we've got to do something recursive. So what that means is that we will go to the next element and see, are we already on the element that we can get? So for example, if we wanted the second one, we'd ask for the second here, we can't get it. If we go down to the next one, ask for the 1th element, again, that's not going to fly. And finally, we'll recurse down to the A and realize that that is now the 0th element that we're looking for. So it's a little bit more complicated, or rather it's a little bit longer to work through. I've also slightly elided over one quite important thing, which is what's at the end of here, because you know, that O wasn't pointing to anything. So one way of thinking about it is that there isn't anything there at all. An element in a linked list can point to another list, or maybe it doesn't. And in fact, that's the way that some programming languages will tend to look at things. But if you think about you know, the word ciao, if you took the first letter off, you'd end up with IAO. And likewise, as you carry on tailing it, you get to an ever smaller string, up until the point where if you try to tail just the string O, what do you get? And obviously you'll get an empty string. So the way that in functional programming languages you usually actually represent these lists is you say there's also a list called the empty list. So actually our linked list looks more like that. It doesn't end at O, it ends with an empty list. And in fact all lists, apart from infinite ones, will end with an empty list. So it looks a little bit like that. So finally, a little bit of Perl. If we look at that, we've got basically two types of lists. So if we're thinking about how to code this in an object-oriented way, we might think about classes, an abstract-based class of list, and it has two types, a normal list and an empty list. These days, we'll tend to use Moose to write object-oriented code, and in Moose people don't very much like abstract-based classes and will tend to go with roles instead. So you can think of it as an abstract-based class. I'm not going to explain what it is now, but basically a list is something that has a head function and a tail function, simply. And the actual linked list would be declared like this. So we'll have a look at that. Because we're talking about purely functional data structures, so which means that we can't actually modify the structures at all. We're declaring these things as read-only. That's what the RO is there for in Moose. And the head of this can be of any type at all, whereas the tail is always going to be a list, i.e. it's going to be one of these linked lists or something else that can be a list. And the something else that can be a list is this empty list, which we've given a head function and a tail function just in case somebody tries to call them on a list, because it's the kind of thing that they might want to do. But all that's going to do is error and say, well, you shouldn't have done that because it's an empty list, and it doesn't make sense to talk about the head or the tail of an empty list. Now, that's not very convenient to use. You can generate a list with that. We could generate chow by doing a very nested expression there that ends with a list empty new, but that's fairly unpleasant. So we'd write a little bit of sugar, a from array method here that'll take a list of characters or whatever and turn it into one of these linked list objects. And once you start with Moose, we may as well go with all the crap we can possibly use. So here's a use of MooseX multi-methods, which is very, very nice. It allows us to have different definitions of from array depending on what we've passed into it. So because we're looking at a kind of recursive thing, we look at what happens if you try to get a list from an empty array. And that class parameter there isn't followed by any data. So we're saying we can do list from array nothing, and all that will return is an empty list. Whereas we've also got a version that's passed a class and a head and some more information, and what that'll do is it'll create a list that links the head with from array of the rest of the list. Or the rest of the array. I'm now confusing list and list, which is a really clever thing to do. So apologies if I'm confusing you guys as well. This will actually work, but if you try and do this, Perl isn't going to be very happy. And I'll explain why. Well, what Perl's going to do is it's going to complain about deep recursion. Well, first of all, it'll complain, and you'll get lots and lots of warnings, and at some point it'll segfault. It might complain and not segfault, depending on how big a list you created. But the reason it'll do that is because within the from array method, we're calling from array. So what's actually happening is we call from array, it calls list link new with from array calls list link new with a from array in it, which again does that and does that 100,000 times. All of these things are kept in memory, so Perl's going to be running out of memory and storing a lot of information because Perl's subroutine calls are quite heavyweight. And eventually, 100,000 levels down, it's going to get an answer. And then it passes the answer back up the list, back up the list, back up the list 100,000 times, and eventually you'll get the answer. So this isn't especially efficient. And you might think, well, does that mean recursion is a very silly technique because you don't want to be having your computer get very slow, warn, and then crash on you every time you create a list of figures. And what a lot of languages do, for example, Scheme, Haskell, all of the functional languages do something called tail call elimination. And they'll basically spot this case and optimize it away. But you can't do that in Perl, because Perl doesn't, or probably, well, I'll say you can't do that and then try and get someone like Matt or Ingi or Dakar to kind of prove me wrong, which would be nice. But I think Audrey did it with GoTo. Yes, it's possible to work around it. What I'm not sure if it's possible to do it automatically. Right. So, okay, first of all, here's some very bad ways of getting around the problem. Let's make it go away by not having the warnings. Now, even if you do that, at some point there's a hard-coded value that Perl will just stop recursing, and you can prevent it from doing that by setting the value to an even bigger number. So that's great, apart from it'll still run very slowly and it'll still segfault when it runs out of memory. So that's a bad idea. But there are some methods. I mentioned Audrey had done one. I think Nothing Much has done something quite similar with GoTo or a couple of techniques. So these tail call routines work in slightly different ways, but they make things work much better. And I'll show you how that will actually work. What it'll do, when we call from array, it'll go to this list link new from array, but it'll actually swap the currently running call for this one, so it doesn't keep the original call hanging around. So instead of the whole thing where we went all the way down, keeping this massive stack of 100,000 calls, we'll end up there with one call, having gone through 100,000 steps, but not keeping hold of them. Then we'll get the result we want, and of course now there's no ladder to go back up again, so we're done at that point. So this is obviously a much better thing to do. Now, how this works, subcall tail has a function called tail, which will basically, instead of calling return, you do tail and then the method, and everything works great. Now the one problem, of course, is I've declared an accessor called tail for this linked list. And so things get very confused, and you have great fun debugging it. So what we have to do is use a nice helper module called subimport that will allow us to import this tail function, giving it a different name. And at that point we can call tail call instead of return. And I have submitted a patch to make subcall tail allow you to import it with a different name, but I don't think it's been incorporated yet. So that will actually now work. So it proves that we can use these recursive routines in Perl to work with linked lists. So this env, so indexing into a list, we can also do in the same way. And we'll do it with multi-methods. So in the case of an empty list, well, it doesn't make sense to try to index into an empty list because it doesn't have any data at all. So we'll just die saying can't index into an empty list. And this is really nice. The multi-methods allow us to give you a where clause. So we can say if we call nth on a list and the value that we've passed in is 0, then we want the element that we're already at. So we'll just return the head of that element. Whereas if the value is greater than 0, then we'll recurse into the list looking for the n-1th position, again using tail call to make sure that we don't blow our stack. Okay, so first of all, I don't know how familiar everyone is with recursion and linked lists. If you are, you're probably cursing me for going over stuff that you did in the first month of computer science, and if you're not, you may be cursing me for baffling you with weird recursive things. So how's everyone feeling about that? Okay. If you have questions, you can ask afterwards or whatever. I'd be interested in feedback because I finished these slides this morning, which means I haven't polished them and worked out exactly what level to be on, so I'd really appreciate feedback. So, I mentioned that we could update a list without mutating anything to protect kittens. And the way you do this with a linked list will be to point, okay, to create a new head there, a new cell called M, pointing at exactly the same list. So we can start off here and have the list meow, and we can be up there and have the list chow, which is quite nice because we share all of, most of that data structure apart from this first character. So that's actually quite nice, and it means that you can change data, but have both versions of it existing at the same time. And this is a really nice feature of purely functional data structures, and it gets even more exciting when you look at trees, which we won't have time to look into now because we've only got another 5 minutes. Of course, if we wanted to make that meow with a W at the end, you might think, oh, that's easy. We just point the O at W and we're sorted. But of course, there's a problem here, because to do that, we'd have to change the value of the O to point its tail, instead of to the empty list, to a W. And that's great, because from here, we now have meow with the W at the end, but we've also now misspelled chow. So mutation can lead to surprising bugs. And this is why people who like purely functional data structures will usually turn their nose up a little bit at mutating data structures. Because you wanted to do something quite reasonable for one data structure, but you've also messed up someone else's. So what you actually have to do here is copy the whole data structure. So you end up having two entirely separate lists. Now, we've had two extremes. One where you had to copy the whole list, and another where you only had to change one cell. So of course, on average, you'll be somewhere in between. You'll have maybe half of the list shared and half of it changing. So for example, if we change something in the middle of this list, so cibo, the Italian for food, this B points to the same O as does ciao, but these two characters have to be copied in order to update that value. And so the lesson there is that everything upstream of a change has to be copied, but downstream stuff can still be shared. And I'm not going to go into that in any great detail, but if you've studied linked lists before, you may have also come across doubly linked lists, where each cell can point back to the previous value. And of course, the problem with that is that you no longer have an upstream and a downstream. So if you make any change anywhere, you have to copy every single element in order to have a purely functional structure. So this makes doubly linked lists very bad data structures for purely functional code. And that's it. So this material is something that I'm working on for a online book called, at the moment, Purely Functional Data Structures for the Working Perl Programmer or something else. It's on GitHub as pure FP book, and at the moment I'm writing the chapter on lists, which goes into more detail than this on zippers, maps, folds, all that good stuff, lots more moose, and so on. And anyone wanted to help or contribute to that, really appreciate it. Thank you very much.
Can you go back one or two slides? Yeah. No, again? Yeah, here. Yeah. So it's upstream and downstream. Why do you have as a T and I in one list and then split up at A and B?
Because if you think of this as being the direction of a river, hence the upstream, downstream, and it's flowing in that direction, yes. Everything that's not being changed in the direction of that flow can be copied. So we can both use that O, because there's nothing that's been changed before that. Whereas here, we know that this B is being changed from A, so we have to copy these cells here. Otherwise, you'd end up having to mutate the data structure.
Oh, you can only point to one element from upstream, but you can't separation.
Yeah.
Oh, okay.
Because if you did, then you'd end up having to overwrite data and mutate it. But yeah, it's quite a fast introduction to it. So, thank you.